Whether a 3-pole or 4-pole fuse disconnect should be used depends on the specific motor configuration and the power distribution system. A 3-pole disconnect is suitable for most alternating current drives. It isolates the 3 phases of the power supply while leaving the neutral or ground connection intact. A 4-pole disconnect is required in specific cases, typically when 1. The drive is directly connected to the incoming plant power without a transformer. 2. The incoming power is supplied by an ungrounded system, meaning no neutral is available. Or 3. The drive motor is a 3-phase, 4-wire system with the neutral connected to the machine frame. In the case of an ungrounded power system or a 3-phase, 4-wire motor connection, a 4-pole disconnect ensures that all 4 conductors are isolated. This prevents the possibility of a neutral conductor being energized when the disconnect is open, which could create a safety hazard. It is recommended to consult with the alternating current drive manufacturer for specific guidance on the type of disconnect required. If the drive is directly connected to incoming plant power without a transformer, and the power system is ungrounded or the motor is a 3-phase, 4-wire system, use a 4-pole fuse disconnect. Otherwise, a 3-pole fuse disconnect is generally sufficient for most alternating current drive applications. Let's delve deeper into the reasons and scenarios where a 4-pole disconnect becomes essential. To fully understand the necessity of a 4-pole disconnect in certain alternating current drive installations, we need to consider the implications of different power system configurations and grounding schemes. The primary function of a disconnect, whether 3-pole or 4-pole, is to provide a safe and reliable means of isolating the electrical circuit feeding the alternating current drive. This isolation is crucial for maintenance, troubleshooting, and ensuring the safety of personnel working on the equipment. Now, let's examine the scenarios where a 4-pole disconnect is mandated. Firstly, when the alternating current drive is directly connected to the incoming plant power without a transformer, a 4-pole disconnect is often required. In this configuration, the drive is exposed directly to the characteristics of the plant's power distribution system. If the power system is ungrounded, meaning that there is no intentional connection between the neutral point of the power source and ground, a 4-pole disconnect becomes essential. In an ungrounded system, the voltage potential of the neutral conductor is not fixed relative to ground. This can lead to unpredictable voltage fluctuations and potential safety hazards. By using a 4-pole disconnect, all 4 conductors, including the neutral, are completely isolated when the disconnect is open. This prevents any possibility of the neutral conductor becoming energized and posing a risk to personnel or equipment. Secondly, a 4-pole disconnect is necessary when the drive motor is a 3-phase, 4-wire system with the neutral connected to the machine frame. In this configuration, the neutral conductor is used to provide a return path for unbalanced loads or harmonic currents. If the neutral conductor is connected to the machine frame, it creates a potential path for current to flow through the frame. This can lead to stray voltages and potential electric shock hazards. By using a 4-pole disconnect, the neutral conductor is isolated along with the 3-phase conductors. This eliminates the possibility of current flowing through the machine frame and reduces the risk of electric shock. Now, let's consider the implications of using a 3-pole disconnect in these scenarios. In an ungrounded system, a 3-pole disconnect would only isolate the 3-phase conductors, leaving the neutral conductor connected. This means that the neutral conductor could still be energized even when the disconnect is open. This creates a potential safety hazard, as personnel working on the equipment could come into contact with an energized neutral conductor. In a 3-phase, 4-wire system with the neutral connected to the machine frame, a 3-pole disconnect would only isolate the 3-phase conductors, leaving the neutral conductor connected to the frame. This means that current could still flow through the machine frame, even when the disconnect is open. This creates a potential electric shock hazard, as personnel working on the equipment could come into contact with an energized frame. In contrast, a 4-pole disconnect provides complete isolation of all 4 conductors, eliminating these potential hazards. Therefore, it is crucial to use a 4-pole disconnect in these specific scenarios to ensure the safety of personnel and equipment. Now, let's talk about when a 3-pole disconnect is sufficient. For most alternating current drive applications, a 3-pole fuse disconnect is generally sufficient. This is because most power systems are grounded, and the neutral conductor is intentionally connected to ground at the service entrance. In a grounded system, the voltage potential of the neutral conductor is fixed relative to ground. This means that the neutral conductor is not likely to become energized even when the disconnect is open. Therefore, a three-pole disconnect, which isolates only the three-phase conductors, is sufficient to provide safe isolation of the electrical circuit. However, it is important to note that even in a grounded system, there may be specific circumstances where a four-pole disconnect is recommended. For example, if the alternating current drive is located in a remote location where the grounding system is not reliable, a four-pole disconnect may be used to provide additional safety. In addition to the power system configuration and grounding scheme, it is also important to consider the specific requirements of the alternating current drive manufacturer. Some manufacturers may require the use of a four-pole disconnect, regardless of the power system configuration. This is because the manufacturer may have designed the drive to operate with a specific grounding scheme, and the use of a three-pole disconnect could compromise the performance or safety of the drive. Therefore, it is always essential to consult with the alternating current drive manufacturer for specific guidance on the type of disconnect required. In conclusion, the decision of whether to use a three-pole or four-pole fuse disconnect for an alternating current drive depends on a variety of factors, including the power system configuration, the grounding scheme, and the manufacturer's requirements. In general, a three-pole disconnect is sufficient for most alternating current drive applications and grounded systems. However, a four-pole disconnect is required in specific cases, such as when the drive is directly connected to an ungrounded power system or when the motor is a three-phase, four-wire system with neutral connected to the machine frame. Always consult with the alternating current drive manufacturer for specific guidance to ensure the safety and performance of the installation. Let's explore a more detailed explanation about grounded and ungrounded systems. Grounded systems provide a low impedance path for fault currents to return to the source, which facilitates the operation of overcurrent protective devices such as circuit breakers and fuses. This helps to quickly clear faults and prevent damage to equipment and reduce the risk of electrical shock. In a grounded system, the neutral point of the power source is intentionally connected to ground, typically at the service entrance. This connection establishes a reference point for the voltage potential of the system, ensuring that the voltage between any phase conductor and ground does not exceed a predetermined limit. This helps to improve the stability of the system and reduce the risk of voltage surges. Ungrounded systems, on the other hand, do not have a direct connection between the neutral point and ground. In an ungrounded system, a ground fault on one phase will not immediately trip a circuit breaker or blow a fuse. Instead, the system can continue to operate with the ground fault present. This can be advantageous in certain applications where it is critical to maintain power continuity, such as in hospitals or industrial plants. However, ungrounded systems also have some disadvantages. One major disadvantage is that they can be more difficult to troubleshoot. Because a ground fault does not immediately trip a circuit breaker, it can be difficult to locate the source of the fault. Another disadvantage of ungrounded systems is that they can be more susceptible to voltage surges. When a ground fault occurs in an ungrounded system, the voltage on the unfaulted phases can rise significantly. This can damage equipment and increase the risk of electrical shock. Due to these reasons, ungrounded systems are less common than grounded systems. When ungrounded systems are used, it is important to implement appropriate safety measures, such as using ground detectors to identify and locate ground faults. Ground detectors can provide an alarm when a ground fault occurs, allowing personnel to take corrective action before the fault causes damage or injury. In addition to the type of power system, the type of motor being used can also affect the choice of disconnect. Three-phase, four-wire motors are commonly used in applications where there are unbalanced loads or harmonic currents. In these motors, the neutral conductor provides a return path for these currents. As mentioned earlier, if the neutral conductor is connected to the machine frame, it can create a potential path for current to flow through the frame. This can lead to stray voltages and potential electric shock hazards. Therefore, it is important to use a four-pole disconnect to isolate the neutral conductor and prevent these hazards. In summary, the decision of whether to use a 3-pole or 4-pole fuse disconnect for an alternating current drive depends on a variety of factors, including the type of power system, the type of motor, and the manufacturer's requirements. It is important to carefully consider these factors to ensure the safety and performance of the installation. Also, consider consulting with a qualified electrical engineer to determine the appropriate type of disconnect for your specific application. A qualified electrical engineer can assess the specific requirements of your installation and provide recommendations based on industry best practices and applicable electrical codes. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others.